Okay, so before going to the break, which is the part I forgot to record actually, so we found out that without using any criteria to determine um, the nature of the point, with whether it's a max or a min. Well, so usually the function is simple enough so we can um, determine whether it's going to be a max or a min. And like in this case, looking at the traces, we get parabolas for each, and both are opening up because of the square terms that are both positive. Well, actually, the graph I did here, it's not correct because that means it would have the vertex at the origin, which is not the case. Actually, it should be shifted 1 unit to the back of the background, if you will, and oh no, one unit to the front and 3 units to the right along the x-axis. So yeah, well, I'm not gonna change the picture. I'd rather just move on to the next part of the section. All right. So we're going to use what we call the second derivative test, also known as the d-test, because we're going to compute a quantity d. That quantity d, which is given by the second partial with respect x times the second partial, or twice with respect x times the second partial twice with respect y, minus any of the mixed partials, that is f with respect x and then y, or y with respect x. It doesn't matter. Recall that they're both the same. Remember Clairaut's theorem, how these two mixed partials are both the same? But we square that term. Okay? So, and then we're going to have 4 different case scenarios. Number one, there's 2 cases in which the quantity d equals to a positive number. So if d is positive and the second partial with respect x at the critical point it's positive, then we are going to have a relative minimum. I mean, think of what you learned back in Calc 1. Calc 1. So the second derivative test, what does that mean? If it's positive, that means concave up, right? Concave up, doesn't that have a minimum point? Right? Okay. So same, but with 2 variables, right? Twice with respect to x. If d is positive and the second partial double with respect to x is this time negative, well then we're gonna have a relative maximum because again, second derivative mean if negative means concave down. Concave down, doesn't that look like having a maximum? So, geometrically makes sense either way. Now, if d is negative, then you don't have to bother and evaluate the second partial at the second partial with respect to x at the given critical point. You just go saddle point. And finally, if d equals to 0, then the test is inconclusive. And well, that was the thing also when we found max and mins using the second derivative test. The test could be inconclusive. And in that case, we should use other methods such as graphing perhaps, or other methods. Yeah, graphing, I guess it's the best. All right? Okay, so let's have a look at one example. Well, actually, use the second partial derivative test to prove that the function in example number 1 has a minimum at the point 1, 3, 4. Okay? Well, so we found the first derivative, the first partial derivative, which were, so f subscript x, that was 2x minus 2, and f subscript y, that is 2y minus 6. Okay, let's find the second partial with respect to x, that is simply 2. The second partial double with respect to y, that's also 2. But we also need the mixed partials. That is, the mixed partial, that is, evaluate f subscript x subscript y, or y and then x. It doesn't matter. What is that going to be? Okay, differentiate 2x squared minus 2 with respect to y. Isn't that going to give us what? 0? Okay, well, so number 1, d, which is f double x times f double y minus f xy quantity squared. Okay, fxx, that equals to 2. times 2 minus 0 squared. That equals 4. Now, is 4 positive or negative? Positive, right? That means D is greater than 0. Also, f double with respect x also equals to 0. Doesn't that tell us that we have a relative minimum? So rather than considering left, right, top, bottom, infinitely many trajectories, which we don't have time for, use the d-test. We're going to use the d-test to determine max, min, saddles, or inconclusive. All right. Okay, let's have a look at another example. Okay, so these are going to get more interesting this time. Okay, so let's consider the function z equals f of x equals to negative 3 e to the negative x squared plus y squared. Well, actually, they're going to be both negative, right? So we can distribute the sign if you want. So negative 3 e to the negative x minus y, negative x squared minus y squared. All right. Okay. So number one, let's find the partial derivatives. Number one, partial with respect x. That equals itself negative 3 e to the negative x squared minus y squared, and by chain rule this is times negative 2x, which will be equal to positive 6x e to the negative x squared minus y squared. Now we need to take the partial derivative with respect y, that is itself negative 3 e to the negative x squared minus y squared times negative 2y this time, because we're differentiating with respect y. And that is going to give us a similar result, but with the y multiplying the exponential. 6y e to the negative x squared minus y squared. Okay? So those are the first partial derivatives. Now we need to create a system of equations. Actually, let's do that later. Let's take the second partial derivatives first. Okay, so let's find f twice with respect x. So we already did the first derivative with respect x. So which differentiation rule do you think we should use to differentiate a second time with respect x? Product rule. So the derivative of 6x, which is 6 times the exponential e to the negative x squared minus y squared, plus the derivative of the exponential, which is going to be itself e to the negative x squared minus y squared times negative 2x, but don't forget the 6x, right? Because this is u prime v plus v prime u, the 6x. It's a product rule in action. Of course, let's clean this up. Okay, let me show you the product rule. U prime v. All this madness is v prime. This is just u. All right. Okay. That'll be then. Simplify this to get f double x equal to 6e to the negative x squared minus y squared minus 12x squared e to the negative x squared minus y squared. All right? So that's only the second partial derivative with respect to x, doubled with respect to x, by the way. Let's get the second partial derivative, in this case, double with respect to y. Okay? So that is f double y. And again, we're going to use the product rule, right? So the derivative of 6y, which is 6 times the exponential, plus the derivative of the exponential, again itself, times negative 2y this time, times 6y. And again, we're going to have a very similar result that we got before, but in this case, the x squared is going to be a y squared. So f double y equals 6e to the negative x squared minus y squared plus, minus 12y squared e to the negative x squared minus y squared. All right. Okay. Yes. Actually, you know what? I think I'm going to factor out the exponential just to reduce, just to make it simple. So e to the negative x squared minus y squared times 6 minus 12 x squared and e to the negative x squared minus y squared times 6 minus 12 y squared. Okay? Yes, especially you might want to do this, especially because when we write the d expression, it's going to look so crazy, and well, the simpler the better. Also, that's going to save us a lot of computations. You'll see. Okay, so we have four partial derivatives. First with respect x, first with respect y, and twice double with respect x and double with respect y. Okay, we need one more, the mixed partial, that is f subscript x subscript y. That is first with respect x and secondly with respect y. That is, this first derivative we did with respect x, let's differentiate it with respect to y now. Do we really need the product rule this time? No, not this time, because the y only appears in the exponent, so it's going to be itself 6x e to the negative x squared minus y squared times negative 2y, which reduces to negative 12 xy e to the negative x squared minus y squared. Okay? So we have everything not yet. We still need to find our critical points. So to get the critical points, create a system of equations where f sub x, f sub y equal to 0. Okay, that means we're going to set what's that? 6x e to the negative x squared minus y squared equal to 0, and 6y e to the negative x minus y squared equals to 0. Well, in this case, we have a non-linear system of equations, and well, because everything is set equal to 0, let's let's use the zero product property. That means, number one, the first equation tells us that either 6x equals to 0 or e to the negative x squared minus y squared equals to 0. The second equation tells us that either 6y equals to 0 or e to the negative x squared minus y squared is equals to 0. We already set the exponential equals to 0. No need to repeat it. So despite the nonlinear system looks ugly, it's really simple to solve. Right? That's because simply x equals to 0 and y equals to 0. But what about the exponential? The exponential never goes to 0, right? So just cross it out. I mean, take a ln on both sides. I'll take it. Take a ln on both sides to get rid of the exponential. Fine. However, that's going to give us an ln of 0 on the right-hand side. What's ln of 0? Undefined. Can we work? Can I add 5 plus 7 minus 3 undefined? We can do arithmetic with undefined. So no critical points, right? I mean, no critical value to that end. So the only legit critical value, critical, not value, point. Put together the x and the y, that's 0, 0. Oh, it's going to be really simple to evaluate. Now let's use the second derivative test to determine whether this point will be a maximum or a minimum, or maybe a saddle point, or maybe the test is inconclusive. 4 case scenarios. Okay, so D, which is f double x times f double y minus fxy or fyx, it doesn't matter, quantity squared. Let's set up the expression. So what did we get for f double x? Okay, I think I have it in handy here. Okay, f double x, it's this expression here that is equal to e to the negative x squared minus y squared times 6 minus 12 x squared. That's f double x. F double y is what I factor out the exponential for over here. That is e to the negative x squared minus y squared times 6 minus 12 y squared minus fxy, all this madness here, that is negative 12 xy e to the negative x squared minus y squared. Everything squared. I know, looks really big. But you're going to love it because a lot is going to get zeroed out. So this is the expression we would use to find the value of d for every single critical point that we have out of solving that system of equations. But for this case in particular, lucky for us, there's only one critical point, and it happens to be all zero. So we need to evaluate d at the point 0, 0. Okay? Evaluate at 0, 0. E to the negative 0 squared minus 0 squared times 6 minus 12 times 0 squared. E to the negative 0 squared minus 0 squared times 6 minus 12 times 0 squared. All right? Minus, 12 times 0 times 0. E to the negative 0 squared minus 0 squared. Quantity squared. Do you guys agree this is going to go to 0? Right? So don't even bother simplify all that. Right? It's going to be 0. And well, what's this going to be? Okay, number one, other simplifications here they're going to come in handy. This is going to be e to the 0, which is 1. This is 0. This is another 1. This is another 0. So we're going to be left with the following. 1 times 6 minus 0, isn't that 6? Times another 1 times 6 minus 0, which is another 6 minus 0, that equals to 36, which happens to be a positive number. 36 is positive, but now because it's either positive or negative, we need to evaluate the second derivative with respect x, double with respect x, to determine the concave up or down, which is going to tell us max or min. So I need to evaluate f double x at the critical point, that equals, so f double, that is e to the negative 0 squared minus 0 squared times 6 minus 12 times 0 squared only. That equals to, is that 6, right? So d is greater than 0 and f double x is also greater than 0. What does that mean? Relative max or relative min? Relative min. So therefore 0, 0 is a relative minimum. All right? However, these results must be expressed as order triples because we want to know what's the maximum or the minimum value, which is the dependent variable. And we get that by evaluating the original function at the critical point. That is f at 0, 0. That is, what was that? 6, right? Negative 3 times e to the negative 0 squared minus 0 squared, that equals negative 3. Relative mean at the point 0, 0, negative 3. Right? So that's another example where we find max and mins. The next one. Let's do another one. I think it's going to be perfect timing for the next example, and then we call it. Okay. Example number 4. Consider the function f of x y equals to xy minus x to the fourth minus y to the fourth Okay, find all relative extrema and saddle points or whatever applies, whatever is applicable here. Okay? So, I mean, we may get rel max, rel mins, I mean, by looking at the function. So, yes, we have even powers for the highest degree terms that look like, not like parabolas, but I mean, yes, likely like parabola, but it's likely smashed because of the size of the exponent. And they're also negative, that means they're going to look upside down. So somehow we're going to have some maximum values there. Well, let's find out if that's the thing here. Okay. Number one, find the first partial derivatives. So that is f with respect to x, that is y minus 4/4 x cubed, that is x cubed. F with respect to y, that equals x minus y cubed. All right? So that is going to be our first partial derivative. So I know I'm not going to take the second partials yet. First, I'm going to go about finding the critical points. So we're going to set the following system of equations. That is y minus x cubed equals 0, x minus y cubed equals to 0. And we need to solve this nonlinear system of equations. It's going to be a fun one, this one, right? So, okay, how are we going to solve this system? Number one, okay, let me rewrite the equations. That means y equals to x cubed and x equals to y cubed. So we need to solve that system of equations. Any ideas how to solve this system of equations? What would you do here? Mm-hmm. Which values?
Either one.
Mm-hmm.
Either one.
Either one. Okay, either one onto the other, I guess. Yes.
Take that x cubed on the top and then plug it in for y on the bottom.
I think either way works, right? So, okay, so in this case, we're going to use the substitution method, right? So to begin with, so we're going to substitute one equation into the other one. Okay, now check this out. This y cubed right here, it's going to be, which is equal to x right here. I'm going to substitute there, but careful because okay, that's going to be okay, substitute this here. That's going to be equal to x, or rather, I'm gonna leave everything in terms of x. Okay, so it's the entire thing here. Whoops. So whoops. I'm gonna replace y right here with x cubed. However, x equals to x cubed. Right? Well, that's going to give us, okay, number one, x equal to x to the 9th power. So we need to solve a 9th degree equation. All right? Okay. Any ideas how to solve this equation? What would you do next? Any ideas?
You have two odd powers. So
Mm-hmm.
one and negative one.
Well, not by guessing. So we need to go algebraically to get these results. I mean, yes, could be, but
You like move like the x to the other side and make an equation.
there you go. A very common mistake in algebra when it comes to this type of equations is to do the following because why not, right? Makes sense. I mean, algebraically makes sense, but do you see the problem there? This is an illegal move because number one, dividing by x itself, we could be potentially dividing by 0, which may or may not be a solution to the equation, right? So if it turns out being a solution to the equation, then it's already an illegal move because we are dividing by 0. Unless somewhere in the problem tells us, they give us a condition that x is not equal to 0, then we're good to go. We can divide by 0, but not in this case. We don't have any additional conditions, or we don't have any physical context that, for instance, maybe this function is modeling the volume or the surface area of a crazy shape, and of course x for sure cannot be 0 because a shape with a 0 length, there's no shape, right? So, but it's not the case, this one. So we need to, in this case, move x to the 9 minus x equal to 0. Solve for x by factoring x times x to the 8th power minus 1 equals to 0. What is this going to give us? Okay, number 1, x equals to 0, or x to the 8th minus 1 equals to 0. Well, x equals 0 is just equal to 0. Do you see how one of the solutions is x equals to 0? So the division by x on both sides, illegal move. X to the 8th power equals to 1, and x equals to the 8th root of 1, which is x equals to 1. Do we all agree with this? Yes?
Wouldn't there be a plus or minus?
Yes, because it's an even power, it's an even index, all right? Plus, minus, all right? So that equals this, all right? So we're going to have 3 solutions. Hold on. Wait. But this is a 9th degree equation. Are we not supposed to get 9 solutions? Okay, well, if you see this equation in a different way. So x times x squared, x to the 8th minus 1, that equals x times x to the 4th minus 1, x to the 4th plus 1, all right? Then keep going with the difference of squares. X squared minus 1, x squared plus 1 times x to the 4th plus 1. And then another difference of squares, x times x plus 1, x minus 1, x squared plus 1, x to the 4th plus 1. Did you see how these last 4 factors right here, or rather, the 2 factors are going to give us 2 complex solutions plus 4 complex solutions? Well, those are the other solutions, but they're complex. In this case, this is real variable calculus. We don't care about those complex solutions. So doing the root property is more than enough, all right? And just take into account the real solutions. Okay, so, okay. Notice how we got 1, 2, 3 critical values. So now we need to get the critical points. And we need to get each for every single critical value. That is 4. X equals to 0. We're going to go back to, what's that? To this equation, y equals x cubed. Y equals to x cubed. So x equals to 0, y equals 0 cubed, which is 0. This is going to give us the critical point 0, 0. All right? Now, let's see what are the critical points related to -1 and +1. Okay, so for x equals to -1, y, okay, again, y equals to x cubed. That's how we're going to get the y value. And y equals to -1 cubed, which is -1. So that's going to give us the point -1, -1. Okay. What else? Okay, one more critical point. For x equals to 1, we're going to use the same y expression, y equals to x cubed, and y equals to 1 cubed, which is 1. That's going to give us the point 1, 1. In this case, we are going to create the d expression and evaluate that d expression for 3 critical points to determine their nature, max, min, inconclusive, or saddle point. Any of those 4 case scenarios. All right, what do we need first? Okay, now that we took the first 2 partials, now let's take f double x, that is the partial derivative of what we differentiated with respect x 1 second time, that is negative 3x squared. The partial derivative of what we already differentiated with respect y. Let's do it a second time with respect y, that is negative 3y squared. And lastly, what we differentiated with respect x, let's differentiate it a second time, but this time it's the mixed partial. Let's differentiate it with respect to the other variable, in this case y, which is simply 1, right? So we have everything we need to establish our expression d, okay? So let's go for it. So d equals f double x, f double y, minus fxy quantity squared. That is f double x, that equals negative 3x squared, f double y, negative 3y squared, minus 1 squared. Let's simplify this. Negative times a negative is positive, 9x squared, y squared, minus 1 squared, which is 1. Okay. So we're going to find or to use this expression for every single order pair. 0, 0, negative 1, negative 1, 1, 1. Let's go about it. Okay. So, number 1. For 0, 0, d at 0, 0, that equals, okay, 9 times 0 squared times 0 squared minus 1. All the first term is going to go to 0. We're going to be left with negative 1. Oh, the value of this negative, what does that mean? Max, min, saddle, inconclusive? Saddle point, right? Saddle point. Okay, we're going to get the z values shortly. I'm going to leave some room for those calculations. So make sure to leave some room, okay? This room is more than enough. So for the point negative 1, negative 1. Okay? That means, okay, d evaluated at negative 1, negative 1. That equals, what's that? 9 times negative 1 squared times negative 1 squared minus 1. Okay, both negative 1 squared are equal to 1. 1 times 1 equals 1 times 9 equals to 9. 9 minus 1 equals to 8. Okay, because d is positive this time, we can potentially have a max or a min. So now we would need to evaluate the second derivative, the double with respect to x, at the given critical point. So let me use f double x, which is this guy right here. All right? Okay, so f double x at the point negative 1, negative 1. Oh, what was f double x? Oh, negative 3 times negative 1 squared. That equals, isn't that negative 3? Okay. So what do we have? D positive and the second derivative negative. That is concave down, which means relative max. Okay. So D greater than 0. Fxx less than 0. Rel max at the point negative 1, comma something. Oh, let me put 0, 0, something. Okay? What's that? Okay. So, and then for the third term, third and last term. For 1, 1, very similar without the minuses, just that. 1, 1. That's 9 times 1 squared times 1 squared minus 1. That's also equal to 8. All right? And again, well, we don't have to repeat the calculation because f double x. Oh, well, no, I need f double x because it's a different point. F double x at 1, 1, that equals negative 3 times 1 squared, which is negative 3. And again, what do we have? Isn't that another relative and maximum? Yep. Because d is greater than 0 and f double x is less than 0. Therefore, we have a real max at the point 1, 1, whatever the z value. So now it's time to calculate the z values. How do we get those z values? Just substituting the original function. So that's why I left a little bit of room here to get those z values. Let me use a different color for that. The original function, that is xy minus 1/4 x to the 4 minus 1/4 y to the 4. So f of 0, 0, that equals 0 times 0 minus 1/4, 0 to the 4th minus 1/4, another 0 to the 4th. Okay? That equals 0. So the z value equals to 0, right? The function value equals to 0. What about the other two values? Okay, f at negative 1, that is negative 1 minus 1/4, negative 1 to the 4th, minus 1/4, negative 1 to the 4th. And simplifying all this, that should give us 1/2. That is 1/2, right? And lastly, for f11, same. 1 times 1 minus 1/4 times 1 to the 4th minus 1/4 times 1 to the 4th, which is again going to give us a 1/2. All right? And those are our results. And again, we need to express this as order triples, and unless we have a different context, of course. And well, let's visualize this in GeoGebra before we leave. Okay, so hey, didn't I open GeoGebra? Where's my keyboard? So there it is. So let me switch to the 3D graphics. We get rid of this plane. And let me type the function. What was that again? Okay, xy minus 1/4 x to the 4th power minus, I need to know the light for better visual, minus 1/4 y to the 4th power. Whoa. There we go. Forgot this, y to the 4th power, and I think that's about it, right? Oh, let me plot the points. The first point, so that's the surface. Can you see the two maximum points? Can you see the saddle, the region where it's a saddle? Okay, let me plot those points just to verify this. That is that 0, 0, 0? That's where the saddle point is, right? And then what about the maximum points? That is negative 1, 1/2. Is that the maximum point? Let me do the other point. Finally, 1, 1/2. There it is. All right. Okay, guys, before you leave, yes, you know, there's another quiz, and then there's another set of notes for tomorrow. Okay, so also let me take attendance. Okay, notes and quiz. It's only one problem, this quiz today, okay? Let me take attendance real quick. All right, Enrique, Alexander, Andrew, sorry, Andrew, Omar, uh, Adrian, Christian, Ferrer, okay, Alexa, Hector, Russell, Lorenzo, Nicolas, Alina, Diego, Dorilyn, Darlene, Garrett, Harmony, Nathaniel, Marco, not here, Diego, Marlene, Daniel, not here, Jose, Stephanie, Carlo, Grisel, Enrique Ruiz, that's you, okay, Enrique, Andy, Diego Sanchez, yeah, that's you, Trevor, Clayton, Julian, and Scott, Sandra, Diego, Priscilla, and Nicolas. All right, guys. That's it for today. So we will finish this tomorrow. Couple more problems, and we move on to Lagrange multipliers afterwards. If you have any questions, I'll be around, or see me at the Math Center.
¿Qué es un saddle point? Es
Un saddle point es como, mira, aquí.
porque se ve como un mínimo. Pero...
Es que si te fijas, si lo ves desde este punto de vista, parece como un máximo desde esta perspectiva, ¿de acuerdo? Pero si lo ves desde este punto, desde esta perspectiva, parece un mínimo. Entonces es como mínimo. Ok, ¿qué es saddle? Saddle es la silla del caballo.
Sí.
Entonces si te fijas en la silla del caballo es como así y así, o como las papitas Pringles también. Sí, es más fácil.
Que
eso.
puede ser entre los dos, ¿no?
Exactamente. Es las dos dependiendo de la traza que utilices.
Ajá, como aquí, el de abajo es para arriba, el máximo, y luego aquí se
Y así, ajá, desde este punto de vista es como un mínimo, pero si lo ves desde este punto de vista
Es un máximo.
es un máximo. ¿Ah?
Okay.
Es más, mira, aquí estas líneas, estas curvitas te lo dicen, mira. Ah, no, bueno, no se ve bien la curvita, pero sí.
Ajá.
Pero además ya con la forma. ¿no?
Okay.
Sí.
I couldn't do this one because I sent you a message.
Yes. Okay, send it to me by tonight.
I don't know.
Yeah, so when they're late, so like we're the ones who get earlier when they get late. Oh, yes. Yeah, like the Baker Valley function, you know, or like R of t, for instance, x naught plus AT, y naught plus PT, z naught plus CT, which is the same as saying everything. This is vector notation, this is parametric notation.
Oh, okay.
But it's the way you get them, or you calculate and get them, it's the same.
Okay.
Right?
Thank you.
I saw the message about the quiz, the wrong quiz. So just this tonight. turn it?
Yeah, submit it. Do you wanna? Okay, you got a PDF.
I can
anyway.
print it.
You can print it. Okay, because I have copies if you want it.
All right, if there's one there, I'll.
Yeah, there's many of them. So. Thank you. What's up, Carlo?
So if I like walk in like at exactly 8 and then I put it here, it's conflict, right?
Okay. Okay, I'm gonna spare you for this one.
Because I don't know if I can come in before 8 because my mom has work and she
Uh-huh.
uses my car. So I
Okay.
have to like wait for her until like 7:40, 7:45.
Mhm.
So I usually come here like 7:55.
Okay, just try your best to get as early as you can. So, but that's fine.
Okay, so for like the last 2 quizzes, those are all smart plate. Like, is that,
Yeah,
like,
well, I didn't know about that. Let's just keep it like that for now, but just for the future, just I mean, either try your best or I'll try to spare you.
What if I like just email you like a picture scan copy?
Did you?
Or if I do it like in the future from now on.
No, just try to get, because it's hard for me to look at emails and then the printed quizzes. Like it's a lot to like manage. So just try your best to be on time.
Okay.
Right?
Thank you.
Take care. Maybe for a little bit, maybe not for too long, because I have an appointment. I may have an appointment like right after. It depends on.
And on Thursday and Friday?
Well, there's no class on Thursday. It's from July 4th, so it's gonna be a long weekend.
Also neither Friday, right?
Yeah, for Fridays it's all we don't open on Fridays, right? Take care. Hmm?